Let's begin with something that feels completely obvious. Time passes. Second after second after second. It feels steady, reliable, universal. If I ask you what time is, you might say, it's what clocks measure. And that sounds reasonable. You look at your phone, the numbers change, and you assume that what's happening on your screen is happening everywhere in the universe in exactly the same way. Right now, as you sit there, time feels like a smooth river carrying everything forward together. You, your house, your city, the moon, the sun, distant galaxies, all drifting along the same invisible current. But that comfortable picture is wrong. Not slightly wrong, fundamentally wrong. For thousands of years, humans assumed time was absolute. The ancient philosophers thought of time as a universal background, a grand cosmic clock ticking away independently of everything else. Later, when Isaac Newton built the mathematical foundation of classical physics, he formalized that intuition. In Newton's universe, time flows, equably without relation to anything external. It doesn't care what happens, it just ticks. That idea feels natural because it matches daily life. If two people stand next to each other, their watches agree. If you leave your house and come back an hour later, everyone agrees that an hour passed. The world appears synchronized, but appearances can be deeply misleading. In the early 20th century, Albert Einstein began pulling at loose threads in physics. First with special relativity, then with something even more radical, general relativity. And buried inside that theory was a claim so strange that even today it's hard to absorb. Time does not flow at the same rate everywhere. The rate at which time passes depends on gravity. That sentence is easy to say, but it should disturb you. It means that time on a mountaintop moves slightly faster than time at sea level. It means that a clock on a satellite ticks at a different speed than a clock on Earth. It means that near something extremely massive, like a neutron star or a black hole, time slows down dramatically. And here's the important part: this is not about perception. It's not that you feel slower. It's not that your brain processes information differently. It's that time itself, the thing your clock measures, changes. If you and I had perfect atomic clocks, and I stood at the bottom of a valley while you climbed a high mountain, and we compared our clocks later, they would disagree. Not because one malfunctioned, not because of a trick, but because gravity actually changed how much time passed for each of us. That is a shocking statement. It contradicts our instincts. It challenges our language. We speak as if now is universal, as if the entire universe shares a common present moment. But according to Einstein's theory of gravity, there is no single universal ticking clock. Each place in the universe carries its own rhythm, and the deeper you look, the stranger it becomes. Because once you accept that gravity can slow time, you're forced to ask a deeper question. What is time really? Is it a thing, a dimension, a physical substance, a bookkeeping device? Einstein's discovery doesn't just tweak Newton's picture. It replaces the stage itself. Time is no longer a rigid background. It becomes something flexible, something that responds to matter and energy. And that means the flow you feel right now, steady, even dependable, is not a property of the universe as a whole. It's a local feature of where you happen to be standing in a curved, dynamic cosmos. So let's ask a very basic question. What is gravity? Most of us were taught a simple story in school. Gravity is a force. The earth pulls you downward. You pull on the earth. The sun pulls on the planets. Everything pulls on everything else. Isaac Newton described this with a precise mathematical law in the 1600s, and it worked beautifully. It predicted the motion of planets, falling apples, cannonballs, tides. In Newton's picture, gravity is invisible but straightforward. Two masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. It's clean, it's powerful, and for centuries it seemed complete. But there was something quietly unsettling about it. Newton himself was bothered by the idea that gravity acted at a distance. If the sun pulls on the earth across empty space, how does it do that? What is physically reaching out from the sun to tug on us? Newton didn't know. He famously said he would not feign hypotheses. The math worked, and that was enough. For a long time, that was enough for everyone. Then Einstein came along and asked a dangerous question: what if gravity isn't a force at all? That sounds almost absurd at first. If gravity isn't a force, why do you feel heavy? Why do objects fall? Einstein began with a simple observation. Imagine you're in deep space, far from any planet or star, inside a sealed box. You are floating weightlessly. Now imagine rockets fire beneath the box, accelerating it upward. Suddenly you feel pressed against the floor. If you drop a ball, it falls to the floor. Everything behaves exactly as if you were standing on Earth. From inside the box, there is no experiment you can do to distinguish between gravity and acceleration. Locally, they are indistinguishable. This idea, the equivalence principle, is the seed from which everything else grows. If acceleration can mimic gravity perfectly, then maybe gravity is not a traditional force. Maybe it is a feature of motion itself. Maybe it has something to do with how objects move through space and time. Now here is where the picture changes completely. Instead of imagining gravity as a pull between objects, imagine space itself is not rigid. Imagine space can stretch, bend, and curve. Not metaphorically, physically. Picture a large rubber sheet stretched tight. Place a heavy bowling ball in the center. The sheet dips. Now roll a smaller marble across the sheet. The marble curves inward toward the bowling ball. Not because the bowling ball is reaching out and pulling it, but because the surface it's rolling on is curved. In this analogy, the sheet represents space. The bowling ball represents a massive object like a planet or star. The marble follows the curved geometry of the sheet. According to Einstein, this is closer to the truth than Newton's force. Mass and energy do not reach out and pull. Instead, they tell space how to curve, and curved space tells objects how to move. But here is the crucial step, the one that leads directly to time slowing down. It's not just space that curves, it's space-time. Space and time are not separate ingredients. They are woven together into a single four-dimensional structure. When a massive object like the Earth sits in space-time, it doesn't just curve space around it. It curves time as well. If the geometry of space-time is distorted, then the paths objects follow through it are distorted. And since every object is always moving through time, that distortion changes the rate at which time passes. Gravity, in this view, is not a mysterious pulling force. It is the shape of reality itself. And if reality bends near mass, then time, woven into that fabric, must bend too. Now we have to confront a concept that sounds abstract but is actually unavoidable. Space and time are not separate things. This is extremely hard to internalize because our senses divide them automatically. You think of space as where things are. You think of time as when things happen. One feels like a stage. The other feels like a clock ticking in the background. But that separation is a habit of perception, not a fundamental truth. Before Einstein, even physicists treated space and time as independent. You could imagine freezing time and still having space. Or imagine removing space while time keeps ticking. They were considered different ingredients of reality. Then something strange happened. When scientists studied the speed of light, experiments in the late 1800s showed that the speed of light is always the same no matter how you move. If you chase a beam of light, it does not slow down relative to you. If you move toward it, it does not speed up relative to you. The speed stays constant. That result makes no sense in Newton's universe. In ordinary life, speeds add. If you throw a ball forward inside a moving train, someone standing outside sees the train's speed plus the ball's speed. But light refuses to behave that way. To preserve the constancy of light's speed, something else had to give. What gave way was absolute time. Einstein realized that if the speed of light is fixed for all observers, then measurements of space and time must adjust depending on motion. Two observers moving relative to each other will disagree about distances and durations. One person's 1 second is not necessarily another person's 1 second. This was the birth of special relativity. But here's the deeper realization. Space and time must be woven together into a single entity so that when one stretches, the other adjusts. Imagine space-time as a four-dimensional fabric. Not just length, width, and height, but length, width, height, and time. Every event that happens, you reading this sentence, a star exploding, a planet orbiting, is a point in space-time. You are not just sitting in space. You are moving through space-time. Even when you are perfectly still relative to the Earth, you are racing through time. In fact, all of us move through space-time at the same overall speed. But that motion can be divided differently between space and time depending on circumstances. If you move faster through space, you move slower through time. That's why fast-moving clocks tick more slowly. And if space-time itself is curved by gravity, then the structure that determines how you move through time is altered. Think of it this way. Imagine space-time as a landscape, not flat, but shaped and contoured. In some regions, the time direction is tilted or stretched. When you exist in that region, your natural path through space-time, what physicists call a geodesic, changes. You are always following the straightest possible path in curved space-time. But if the geometry itself is warped, then what counts as straight changes. Near a massive object, the geometry of time is distorted. The intervals between moments are stretched compared to regions far away. And because you are embedded in that geometry, your clock, which is just a physical process unfolding in time, must follow that distortion. The slowing of time near mass is not an added effect. It is not a secondary consequence. It is built into the architecture of space-time itself. Once you see space and time as one connected structure, gravitational time dilation stops being mysterious. It becomes inevitable. If mass bends space-time, and you live inside space-time, then the rate at which you experience time cannot remain uniform everywhere. Time is not flowing over the universe like an invisible river. It is part of the terrain. Let's return to the elevator because it contains one of the deepest insights in physics. Imagine you are inside a completely sealed elevator. No windows, no information about the outside world. At first, the elevator is floating in deep space, far from any stars or planets. You feel weightless. If you let go of a ball, it just hovers beside you. You drift gently, effortlessly. Now suppose rockets attached to the bottom of the elevator fire, causing it to accelerate upward. Immediately you feel something change. Your feet press against the floor. The ball you release falls downward and hits the floor. If you jump, you land back where you started. Everything behaves exactly as it would if you were standing on Earth. From inside that sealed box, you cannot tell whether you are in a gravitational field or simply accelerating upward. This is not a trick. This is a profound statement about nature. Einstein realized that gravity and acceleration are locally equivalent. This is called the equivalence principle, and it is the conceptual foundation of general relativity. Now let's push the thought experiment further. Imagine you shine a flashlight horizontally across the elevator while it is accelerating upward. From your perspective inside, the beam of light will appear to curve downward slightly before it hits the opposite wall. Why? Because while the light is traveling across the cabin, the elevator is moving upward, so the wall rises to meet the beam. But if acceleration and gravity are indistinguishable, then the same thing must happen in a gravitational field. Light passing through a gravitational field must bend. This is a shocking conclusion. Light has no mass, yet gravity affects it. And if gravity can bend light, then gravity must be altering something more fundamental than just the motion of massive objects. It must be altering the structure through which light travels, space-time itself. Now here is where time enters the picture in a subtle but unavoidable way. Imagine you place two identical clocks inside the accelerating elevator. One is on the floor, one is on the ceiling. Because the elevator is accelerating upward, light signals sent from the floor to the ceiling will experience a tiny shift. By the time the light reaches the top clock, the ceiling has gained a bit of speed. Careful analysis shows that the clock on the floor and the clock on the ceiling will not agree about the passage of time. The lower clock will tick more slowly relative to the upper one. If acceleration causes clocks at different heights to tick at different rates, and acceleration is indistinguishable from gravity, then gravity must also cause clocks at different heights to tick at different rates. This is gravitational time dilation emerging directly from the equivalence principle. You don't need complex equations to see the logic. If gravity is equivalent to acceleration, and acceleration changes how light signals behave between different points, then gravity must change how time behaves between different points. On Earth, this effect is tiny. A clock at your feet runs slightly slower than a clock at your head. The difference is extraordinarily small, but it is real and measurable with precise instruments. The deeper the gravitational field, meaning the closer you are to a massive object, the stronger this effect becomes. What makes this idea so difficult is that nothing feels different locally. Your biological processes, your thoughts, your heartbeat, everything proceeds normally. You cannot feel your own time slowing. Time only reveals its flexibility when you compare clocks in different gravitational potentials. And that comparison exposes something radical. Gravity does not merely influence motion. It reshapes the rate at which reality unfolds. Now we're ready to ask the central question in a more precise way. Why exactly would time slow down near a massive object? It's easy to repeat the statement mass curves spacetime, and curved spacetime changes how clocks tick. But if we want to really understand it, not just memorize it, we need to build an internal picture. Let's try to construct one carefully. Imagine spacetime as a kind of landscape, not a flat floor, but a terrain with hills and valleys. In everyday life, the terrain around us is only very slightly curved, so we don't notice it. But near a massive object, like a planet or star, the terrain dips downward. When we use the rubber sheet analogy, we usually focus on how objects roll inward because of the curved surface. That helps explain why planets orbit stars. But the analogy is incomplete because it only shows space bending, not time. To bring time into the picture, imagine that every point in this landscape has a built-in clock. These clocks measure the natural flow of time at that location. If the terrain were perfectly flat, all the clocks would tick at the same rate. But near a massive object, the landscape is not flat, it curves downward. And that curvature affects not only distances, but also the intervals between moments. Here's a more physical way to think about it. In physics, time is not an abstract concept floating above reality. Time is measured by physical processes. A clock is just a repeating physical event, the vibration of a quartz crystal, the swing of a pendulum, or the oscillation of atoms in an atomic clock. If gravity changes the structure of space-time, it changes the environment in which those physical processes occur. The oscillations of atoms, the transitions between energy levels, the ticking of any mechanism, all of them unfold within space-time. If the geometry of time itself is stretched, those processes take longer when viewed from far away. Another way to see it is through energy. To lift an object away from a planet, you must give it energy. That's because it sits in a gravitational potential well, like a ball resting at the bottom of a valley. Climbing out requires work. Light also loses energy when climbing out of a gravitational field. This is called gravitational redshift. When light escapes from near a massive object, its frequency decreases and its wavelength stretches. But frequency is just cycles per second. If light emitted near a massive object has a lower frequency when measured far away, that means the seconds near the massive object are longer. The clock that produced those light waves was ticking more slowly. So gravitational time dilation is not an isolated phenomenon. It is connected to gravitational redshift, energy conservation, and the geometry of space-time itself. All these pieces fit together consistently. Near Earth, the effect is tiny because Earth's mass, while enormous by human standards, is small compared to stars or black holes. The difference between a clock on the surface and a clock in orbit amounts to microseconds per day. But scale up the mass, compress it into a smaller region, and the effect grows dramatically. Near a neutron star, time runs noticeably slower. Near a black hole's event horizon, time slows to an extreme degree. To a distant observer, a clock approaching the event horizon appears to tick more and more slowly, asymptotically approaching a standstill. And here is the important point. This is not because something is physically resisting motion. It is not friction. It is not drag. It is not a force slowing down gears. It is geometry. The structure of space-time determines how much time passes between events. So when we say time runs slower near a massive object, what we really mean is this. The shape of space-time near mass alters the length of time between ticks, just as it alters the length of paths through space. Time is not immune to gravity. It is shaped by it. This idea is not just theoretical. It has been measured directly and repeatedly, proving that gravitational time dilation is real, not hypothetical. We can place atomic clocks, which are the most precise timekeeping devices ever created, at different heights and compare them. Even over a difference of a few meters, the clocks disagree. The one closer to Earth's surface ticks more slowly, exactly as predicted by Einstein's equations. The discrepancy is tiny, fractions of a billionth of a second per second, but it is measurable and consistent. Every experiment confirms the prediction. One of the most dramatic confirmations comes from satellites orbiting the Earth. GPS systems rely on ultra-precise timing to calculate positions. Each satellite carries an atomic clock. These clocks are farther from Earth's center, where gravity is weaker, and they are moving at high speeds relative to observers on the ground. Both effects, the weaker gravity and the high speed, cause the satellite clocks to tick faster or slower relative to clocks on Earth. If engineers did not correct for these relativistic effects, GPS would be useless. Positions would drift by kilometers in a single day. Humanity's ability to navigate streets, oceans, and skies depends on the validity of Einstein's theory. This is not abstraction. It is applied physics at a global scale. Airplanes provide another demonstration. High-precision atomic clocks flown around the world in different directions confirm both special and general relativity. Clocks on planes traveling eastward or westward, compared with clocks left on the ground, show tiny but measurable differences. These experiments reveal that time is not universal but local, dependent on motion and gravity. Even though the differences are imperceptible in daily life, they are significant for systems that demand extreme accuracy. Gravitational time dilation becomes extreme near very massive objects, such as neutron stars or black holes. In these environments, the curvature of space-time is so intense that time passes dramatically slower near the object compared to a distant observer. If you hovered near the surface of a neutron star, while a friend watched from far away, you would age more slowly. Seconds for you would stretch into much longer intervals for the distant observer. Near the event horizon of a black hole, this effect reaches its maximum. To a distant observer, it appears as if time almost stops for an object approaching the horizon. Light leaving the region becomes increasingly redshifted, fading into invisibility. The difference is not a matter of perception or illusion. It is the fabric of reality behaving according to the laws of space-time. These effects show that time is flexible, not absolute. It adapts to the geometry of space-time, shaped by mass and energy. Our intuitive sense of a uniform flow of seconds is limited to small regions of weak gravity, like the surface of the Earth. Once we consider other places, especially regions of intense gravity, the universality of time dissolves. Time is not a backdrop against which events happen. It is an active component of the universe's architecture, bending and stretching according to the distribution of matter and energy. The fact that gravitational time dilation is real, measurable, and essential for modern technology reinforces its significance. We are not dealing with speculation or metaphor. We are dealing with the structure of reality itself. Every GPS calculation, every satellite orbit, every atomic clock comparison is a testament to the truth of Einstein's insight. Time is not absolute. It bends, it stretches, it is local. Our ordinary experience hides this truth, but technology and observation reveal it. Time is alive with geometry shaped by the universe and intimately connected to mass and energy. To understand the full impact of gravitational time dilation, we need to consider extreme environments, places where the effect is no longer tiny and subtle, but becomes overwhelming. Black holes represent the ultimate example. These objects are incredibly massive and compressed into a tiny region of space, so dense that nothing, not even light, can escape once it crosses the event horizon. Near such an object, the curvature of space-time is enormous, and the flow of time is distorted beyond ordinary human intuition. Imagine approaching a black hole. From your own perspective, you descend normally. You feel your body functioning, your heart beating, your thoughts racing at their usual pace. Seconds tick by just as they always have. But if someone were watching you from far away, the story is very different. As you get closer to the event horizon, your movements appear to slow down. Every motion, every tick of your clock stretches out. To the distant observer, it looks as though time itself is crawling for you, approaching a standstill at the horizon. You do not feel the difference, but your timeline is diverging from theirs dramatically. The light you emit carries this story. It is stretched, its frequency lowered, becoming redder and fainter as it climbs out of the gravitational well. Eventually, to the distant observer, you would fade from view, frozen in the last moment before the horizon. From your own vantage point, nothing unusual seems to happen. You cross the event horizon in finite proper time, still experiencing time normally. There is a stark tension between perspectives you experience, and the view from far away are fundamentally incompatible, yet both are valid in their own frame of reference. Neutron stars provide a slightly less extreme, but equally striking example. These remnants of collapsed massive stars are incredibly dense, packing a mass greater than the Sun into a sphere, only about 20 kilometers across. The gravitational field at the surface is immense. A clock on the surface of a neutron star would tick significantly slower than one far away in empty space. A human standing on that surface would age more slowly compared to someone orbiting the star at a safe distance or watching from afar. This is not science fiction. It is a direct consequence of the geometry of space-time and has been calculated precisely using Einstein's equations. The magnitude of the effect depends on two factors: the mass of the object and the distance from its center. Larger mass and smaller radius produce stronger gravitational time dilation. Earth is massive enough to produce a measurable effect, as confirmed by experiments with atomic clocks on mountains and satellites. But objects like neutron stars and black holes push this phenomenon to the extreme, revealing the flexibility of time in ways that challenge our intuition. These environments also highlight the relational nature of time. There is no universal no that all observers share. Each location in space-time experiences its own rate of temporal flow, depending on the curvature produced by mass and energy. An observer far from a black hole will see your time stretch toward infinity as you approach the event horizon, while you yourself experience finite, ordinary time. This relativity of simultaneity is a radical departure from our everyday assumptions. It shows that the universe does not tick uniformly. Each observer carries their own personal tempo, determined by where they are and what gravitational influences they experience. In essence, extreme gravitational environments like neutron stars and black holes make visible what is always true, but usually imperceptible time is not an absolute, uniform backdrop. It is a dynamic part of the universe, molded by mass and energy. These examples push our understanding beyond ordinary experience, forcing us to confront a reality where the passage of time is flexible, relative, and profoundly shaped by the structure of space-time itself. What do we actually know about gravitational time dilation, and why does it matter? We know that gravity curves space-time. This is not a guess or a metaphor. It is a precise, quantitative description confirmed by countless experiments. Einstein's equations provide an exact mathematical framework for predicting how mass and energy warp space-time. Within that framework, the slowing of time near massive objects is not optional or approximate. It is required. The math dictates it, and nature has verified it repeatedly. Atomic clocks provide one of the clearest confirmations. These clocks count the oscillations of atoms with extraordinary precision. Place two identical clocks at different gravitational potentials, one at sea level and one at the top of a mountain, and they will no longer agree. The clock closer to Earth's center ticks more slowly. Even though the effect is minuscule in daily experience, it is real and measurable. Modern instruments can detect differences of billionths of a second per second. In laboratories, physicists have repeated these measurements, varying the height, using different types of clocks, and observing perfect agreement with the predictions of general relativity. Satellites orbiting the Earth demonstrate the practical importance of gravitational time dilation. GPS satellites travel in weaker gravitational fields than the surface of the Earth. If their onboard clocks ticked at the same rate as clocks on the ground, positional errors would accumulate rapidly, leading to navigational chaos. Engineers must correct for both gravitational time dilation and special relativistic effects caused by satellite motion. Without these corrections, GPS devices would be useless within a day. Humanity relies on gravitational time dilation every day, whether we realize it or not. The theory is not abstract. It is the backbone of precision technology. Airplanes have provided a further, compelling demonstration. When high-precision atomic clocks are flown around the world, moving eastward and westward, they accumulate tiny differences compared to stationary clocks. These differences are exactly what relativity predicts, accounting for both motion and altitude. Experiments like these have been repeated dozens of times over decades, confirming the predictions consistently. Our technological infrastructure depends on the accuracy of these effects, and our scientific understanding is strengthened by the fact that we can measure such tiny deviations from intuition. Gravitational time dilation becomes dramatically more pronounced near dense, massive objects like neutron stars and black holes. In these regions, the flow of time for a local observer can differ drastically from that experienced by a distant observer. A clock near the surface of a neutron star may tick far more slowly than one in open space. Near the event horizon of a black hole, the slowing of time becomes extreme. To a distant observer, a falling object appears to freeze at the horizon, its emitted light stretched toward invisibility. Yet from the object's own perspective, time continues normally, illustrating the relativity of simultaneity and the deeply local nature of temporal flow. All of these observations converge on a single point. Time is flexible, not absolute. It adapts to the geometry of spacetime, which is shaped by mass and energy. The intuitive idea of a universal, no, is false. Every observer, depending on position and motion, experiences their own rate of temporal flow. Time is woven into the structure of the universe, and that structure is dynamic and interactive. We also know what we do not know. While general relativity provides a complete description of gravitational time dilation, we do not understand the fundamental nature of space-time itself. Is it continuous or discrete? Is time a fundamental aspect of reality, or does it emerge from deeper physics we have yet to discover? We do not know how to reconcile this understanding with quantum mechanics fully. What happens inside a black hole at the singularity remains a mystery. The theory works beautifully up to extreme conditions, but the ultimate fabric beneath time remains elusive. What is certain is that time is not the same everywhere, and this realization is confirmed, measured, and applied in daily technology. Time bends, slows, and stretches according to mass and gravity. It is not just a theoretical curiosity, it is woven into the architecture of the universe itself, a flexible dimension intimately tied to the matter and energy around it. Even though we can describe gravitational time dilation mathematically and measure it precisely, there are profound aspects of time and gravity that remain mysterious. We know that space-time curves in the presence of mass and energy, and we know that clocks in stronger gravitational fields tick more slowly relative to those in weaker fields. These predictions have been confirmed repeatedly, from atomic clocks on Earth to satellites orbiting high above. Yet when we ask deeper questions, the answers become elusive. We do not know what space-time fundamentally is. Einstein treated it as a smooth, continuous fabric, something that can bend and stretch, but essentially exists as a stage for matter and energy. Modern physics suggests that this may be an approximation. Quantum mechanics which governs the behavior of particles at the smallest scales, does not play nicely with the smooth space-time. Attempts to combine general relativity and quantum mechanics into a single unified theory, sometimes called quantum gravity, run into profound mathematical contradictions. These contradictions suggest that our current understanding of space-time, and consequently of time itself, is incomplete. We do not know why mass curves space-time. We can describe it, we can calculate it, but we cannot explain why this happens at the most fundamental level. Mass, energy, and momentum are properties of matter, and space-time reacts to them. But what is the mechanism, if any, beneath this reaction? Is space-time a kind of field that responds dynamically, or is it emergent from something even more fundamental? These are questions without answers. We also do not fully understand what happens to time inside extreme gravitational environments, like black holes. As an object approaches the singularity at the center, the equations of general relativity break down. Time and space, as we know them, lose meaning. Does time cease? Does it reverse? Or is there a deeper structure we cannot yet perceive? These are not simply technical problems. They are conceptual challenges that force us to reconsider what we mean by time in the first place. We do not know how time connects to quantum mechanics. Quantum physics treats particles and energy in probabilistic terms, with no clear continuous flow of time in the traditional sense. Meanwhile, general relativity treats time as a smooth dimension affected by gravity. Reconciling these two pictures is one of the greatest open questions in physics. Without a theory that unites them, we cannot fully understand the origins or the ultimate fate of time. We do not know whether time is fundamental or emergent. Some theoretical physicists propose that time may arise from relationships between events or from the entanglement of quantum states, rather than existing as an independent, pre-existing entity. In this view, time is a derived concept, an emergent property of deeper physical processes. But these ideas remain speculative, with no experimental confirmation so far. Our struggle to understand time is partly cognitive. Human brains evolved to track short-term events, recognize patterns, and predict consequences in our immediate environment. Our intuitions are tuned to everyday scales, where time feels absolute and steady. When confronted with extreme gravity, curved space-time, or the bizarre predictions near a black hole, our minds strain to comprehend. Intuition fails, language fails, and even imagination falters. Despite these unknowns, we can be confident about what we do know. Time bends, it stretches, it is affected by gravity, and it is measurable. Gravitational time dilation is real, and it is a part of the universe we inhabit. Yet the ultimate nature of time, what it is at the deepest level, why it exists, and how it emerges from the fabric of reality, remains one of science's most profound mysteries. The more we learn, the more we realize that time is far stranger and more flexible than our everyday experience suggests, and that understanding it fully will require a revolution in how we think about reality itself. Our difficulty in grasping the nature of time is not just a matter of incomplete knowledge. It is also a consequence of how humans experience reality. Our brains evolved over millions of years to survive on a planet where gravity is relatively uniform and where time passes at nearly the same rate everywhere we go. We needed to recognize patterns, anticipate the behavior of prey or predators, and coordinate actions with other humans. In that context, assuming that time flows at a steady, universal rate was perfectly adaptive. It worked for hunting, gathering, and navigating daily life. It built intuition, habits, and language that rely on a uniform now. But this intuition is a trap when it comes to extreme environments or cosmic scales. We are not equipped to perceive the curvature of space-time, the stretching of seconds near a neutron star, or the relative ticking of clocks in orbit versus on Earth. These are not abstract or theoretical curiosities. They are fundamental aspects of reality, but they lie far outside the evolutionary pressures that shaped our senses and thinking. Our minds evolved to interpret small, local scales, not the immense curvature of the universe. That is why gravitational time dilation feels counterintuitive, even shocking. Every attempt to explain it using everyday metaphors runs into limits. Saying that time slows down or stretches risks misunderstanding, because time itself is not a substance or fluid. It is part of the very structure through which matter moves. We can feel and measure the effects through clocks, but our perception cannot directly sense the bending of time. This disconnect between experience and reality is part of why humans struggle to internalize the concept. Physics can describe it in equations, but translating that description into intuition is profoundly difficult. Our struggle is compounded by language itself. Words like now, later, and instant assume a universal present, when physics tells us that what is simultaneous in one location is not simultaneous in another. These words lose their precise meaning. The universe does not share a single clock. There is no universal. No. Each observer carries their own temporal rhythm, determined by their position in space-time and the gravitational influences they experience. We can calculate these differences, measure them with extreme precision, and even apply them in technology like GPS, yet they remain alien to our natural intuition. This challenge is more than cognitive. It is also philosophical. Gravitational time dilation forces us to reconsider what we mean by past, present, and future. Events that appear simultaneous to one observer may unfold at very different rates for another. Our ordinary notions of causality, sequence, and simultaneity are local approximations, useful only within weak gravitational fields and everyday speeds. Outside that context, the universe operates according to a more complex geometric logic. Time is not a background container for events. It is a dynamic participant in the unfolding of reality. Accepting this requires humility. Humans naturally want simple, universal rules. We want clocks that tick the same everywhere, a cosmic schedule that all observers share. Reality refuses to comply. It is not obliged to be intuitive, convenient, or comfortable. Time bends according to gravity. The universe is not a rigid, predictable machine. It is a flexible structure in which each location, each mass, each gravitational field influences the rate at which events unfold. The struggle to comprehend this is the struggle to align human intuition with the deeper geometry of the universe. It reminds us that knowledge is never complete, that experience is limited, and that reality often defies instinct. The fact that we can measure, predict, and apply the effects of gravitational time dilation, even without feeling them directly, is a triumph of human reasoning. Yet the difficulty we have imagining it shows the gulf between perception and the true nature of time, a gulf we continue to explore step by step, equation by equation, observation by observation. Imagine a pair of twins identical in every way, born at the same time and raised in identical environments. For simplicity, one twin remains on Earth, living a life of ordinary gravity, while the other is sent on a journey to the surface of a neutron star, an incredibly dense stellar remnant with gravity billions of times stronger than Earth's. Both experience life normally in their own locations. Their hearts beat, their thoughts unfold, their clocks tick as they always have. Yet when they reunite, a startling difference emerges. The twin who ventured near the neutron star has aged far less than the twin who stayed on Earth. From the perspective of the twin on Earth, the other moved through time more slowly. This is not metaphor or exaggeration. It is a direct consequence of the geometry of space-time and the effect of gravitational time dilation. This scenario is often called the twin paradox. And while it is usually discussed in the context of high-speed travel under special relativity, the same principle applies with gravity under general relativity. Time is not a universal, evenly flowing dimension. It is local. It depends on where you are and the gravitational field in which you exist. A second is not the same second everywhere. Each twin experience time normally in their own frame of reference. Yet when compared across frames, the difference becomes evident. The paradox challenges our intuition because we are used to assuming a single, shared timeline for all observers. But in a relativistic universe, there is no absolute simultaneity. Even in less extreme scenarios, the principle holds. Consider someone living at the top of a mountain versus someone at sea level. The difference in gravitational potential causes the higher altitude individual's clock to tick slightly faster. Over a lifetime, the effect is measurable. In satellites orbiting Earth, the difference is corrected to ensure technologies like GPS function correctly. These small differences illustrate the universality of the principle. Gravitational time dilation occurs wherever there is a gradient in gravitational potential, even if the effect is imperceptibly tiny to human senses. The twin thought experiment illustrates that time is not merely a background in which events unfold. It is part of the architecture of reality itself. Each observer's experience of time is shaped by their position in spacetime. This means that the age, lifespan, and experience of events are inherently local phenomena contingent on the geometry of the universe around you. It is a radical departure from pre-Einsteinian thinking, where one could assume a shared cosmic clock ticking the same for everyone. In our modern understanding, there is no single universal. Now, every observer carries their own temporal flow, and these flows may diverge dramatically in the presence of extreme gravity or high velocity. This realization also has practical consequences. Astronauts aboard the International Space Station, orbiting Earth at high speed, and experiencing slightly weaker gravity than on the surface, age just a tiny fraction of a second less than those on Earth over months of orbit. These small effects become larger near massive bodies, illustrating that gravitational time dilation is not merely theoretical. It is measurable and operational. The philosophical implication is profound. The passage of time is relative, not universal. Each observer, whether on Earth, a neutron star, or orbiting a black hole, experiences time according to the curvature of space-time at their location. Life itself, aging, experiences memory, proceeds at different rates depending on your position in the cosmos. This challenges our ordinary intuitions and forces us to reconsider the very meaning of time, simultaneity, and personal experience. In a relativistic universe, the flow of life itself is a local, dynamic phenomenon intimately tied to the geometry of the universe. The twin thought experiment highlights a fundamental truth. Time is not universal, and the flow of events depends intimately on the gravitational environment. But this principle extends far beyond thought experiments and extreme astrophysical scenarios. It shapes reality at every scale. Even here on Earth, subtle variations in gravitational potential affect the passage of time. A clock at the bottom of a deep mine ticks ever so slightly slower than one on the surface. Atomic clocks at high altitude laboratories tick faster than identical clocks in valleys. These differences, though imperceptible without precise instruments, are real and measurable, showing that gravitational time dilation is not an exotic phenomenon. It is woven into the fabric of everyday life. Technological systems rely on this understanding. The Global Positioning System, or GPS, would fail catastrophically if engineers ignored gravitational time dilation. Satellites orbiting Earth experience weaker gravity than the surface, and their onboard clocks tick faster as a result. At the same time, their motion relative to Earth introduces special relativistic time dilation, causing clocks to tick more slowly. Both effects must be calculated and corrected to within nanoseconds to ensure accurate positioning. Humanity's ability to navigate continents, oceans, and skies depends on our ability to measure, understand, and correct for the flexibility of time. Gravitational time dilation is not just a theory, it is an operational reality that underpins modern civilization. Extreme environments magnify the effect dramatically. Near neutron stars, a second for a distant observer may encompass minutes or hours for someone close to the star's surface. Near black holes, the difference becomes even more extreme. To an outside observer, an object falling toward the event horizon seems to freeze in time, light stretching and fading, red shifted into invisibility. The person falling in experiences ordinary time, yet their future becomes almost unreachable to distant observers. The divergence of temporal experience in these environments demonstrates that time is a local relational quantity contingent on mass and gravity rather than a universal backdrop. This relativity of time has deep implications for how we think about reality. Our ordinary sense of a shared present is limited to weak gravitational fields and slow speeds. Beyond these conditions, simultaneity becomes relative. Two observers in different gravitational potentials or moving at different velocities cannot agree on what events are simultaneous. This does not mean one observer is wrong. It means the universe itself does not enforce a single timeline. Time is not an external container that events unfold within. It is an intrinsic part of the universe's geometry, inseparable from space, matter, and energy. Understanding this requires a shift in perspective. Time is flexible, local, and interactive. Every mass bends the passage of time, and every observer experiences it differently depending on their location. Aging, memory, causality, and sequence are all local phenomena shaped by spacetime. Life unfolds according to these local rhythms. In a relativistic universe, the flow of existence is not uniform or absolute. It is dynamically entwined with the structure of reality. This challenges intuition, defies common experience, and stretches the imagination. But it is precisely what makes the universe astonishingly rich and subtle. Gravitational time dilation teaches that reality cannot be fully grasped through human intuition alone. Observation, measurement, and mathematics reveal truths that our senses cannot perceive. Time, once assumed absolute, is revealed as relative, shaped by mass, energy, and motion. The very idea of a universal no dissolves. Life and events are experienced differently depending on location in the cosmos. This insight reshapes our understanding of reality, showing that the universe is more intricate, flexible, and wondrous than our everyday perceptions suggest. Time is alive with geometry, and existence unfolds according to its curvature.